In the previous video, we looked at graph autoencoders. The key idea was simple. A GAE maps each node to one fixed latent embedding. So for every node, the model learns one deterministic vector z. Variational graph autoencoders change exactly this part. Instead of saying this node has one fixed embedding, a VGAE says this node has a distribution of possible embeddings. This distribution is described by a mean, mu, and a spread, sigma. So the main shift is from fixed embeddings to probabilistic embeddings. This allows the model to represent not only where an embedding should be, but also how uncertain it is. Now we take the same autoencoder idea and make one important change. In a normal graph autoencoder, the encoder gives each node one fixed embedding. But in a variational graph autoencoder, the encoder does not output only one vector. Instead, it outputs the parameters of a distribution. The first parameter is mu. It tells us where the embedding is centered. The second parameter is sigma. It tells us how much uncertainty or spread we have around that embedding. So the latent space is no longer just a set of fixed points. It becomes a space of distributions. The decoder still has the same job. It uses the latent representation to reconstruct the graph. But now this latent representation is probabilistic. So the encoder becomes probabilistic. Instead of producing one exact latent vector, it predicts two parameters. Mu gives the center. Sigma gives the spread. Together, they define a distribution for the latent variable z. So the model no longer commits to one exact point. It learns a region in latent space where the embedding is likely to be. Now we move to the latent representation. On the left, we show three example graphs. The first two graphs are almost the same, only a small connection changes. The third graph has a clearly different structure. After the encoder, each node is no longer represented by one fixed vector. Instead, each node gets its own small distribution. This is what the small ellipses in the middle represent. Then we apply pooling. Pooling collects the node-level information and summarizes the whole graph into one graph-level distribution. On the right, we visualize these graph-level distributions in a two-dimensional latent space. The blue and green distributions are close to each other because the corresponding graphs are also very similar. The purple distribution appears in another region because the third graph has a different structure. So the key intuition is this. A VGAE does not only learn where an embedding is, but also how uncertain this embedding is. And in the latent space, similar graphs should lead to nearby distributions, while different graphs should be separated. Now we come to the most important technical idea in a VGAE, the reparameterization trick. The encoder does not directly output one latent vector. Instead, it outputs the parameters of a distribution, the mean mu and the standard deviation sigma. This distribution tells us where the latent embedding should be and how much uncertainty we allow around it. To pass something into the decoder, we still need one concrete latent vector z. So the simple idea would be sample z directly from this distribution. That is what we show here with the yellow dots. One of these possible samples is selected and passed forward to the decoder. But this creates a problem during training. Sampling is random, and if we sample directly from the distribution, the gradient cannot flow cleanly through this random step. So the model would have difficulty learning how mu and sigma should change. The reparameterization trick fixes this. Instead of sampling z directly, we sample a separate noise variable epsilon from a standard normal distribution. Then we construct z using the formula z equals mu plus sigma times epsilon. So the randomness is now isolated in epsilon. Mu and sigma are still normal differentiable outputs of the encoder. This means the model can sample latent vectors, but gradients can still flow back to the encoder. That is the key point. VGAE keeps the probabilistic latent space, but still remains trainable with gradient descent. After sampling z, the The decoder works almost like in a normal GAE. It takes Z and reconstructs the adjacency matrix A hat. Then A hat is compared with the real adjacency matrix A. This gives the reconstruction loss. It checks whether the original edges were recovered correctly. But VGAE adds one more term, the KL regularization. The KL term keeps the learned distributions close to a simple standard normal prior. I also have a separate shorts video where I explain the KL term more intuitively. So the VGAE loss has two goals: reconstruct the graph well and keep the latent space smooth and organized. Let's summarize the main idea. A standard GAE learns fixed embeddings and trains mainly through reconstruction loss. A VGAE extends this by learning distributions over embeddings. This gives us a probabilistic latent space. The reconstruction term still helps recover the graph structure. The KL term keeps the latent space smooth and regular. So compared to a GAE, a VGAE can model uncertainty more explicitly and learns a more organized latent representation. That is the core idea behind variational graph autoencoders. Thanks for watching. In the next video, we will compare different graph neural network architectures, like graph convolutional networks, graph attention networks, graph isomorphism networks, and so on. Then we will see how these architectures change the encoder inside a graph autoencoder. See you in the next one.